So we know we need partial fractions here because they already split this for us, actually. I'm going to need to get two separate fractions for these two separate factors. So I'm going to write this off to the side. And I want this to be something over 2x minus 3 plus something over x plus 2. And so if we multiply every term by this common denominator, here they're going to both cancel out. So that'll just be 7x. And over here we'll have a times x plus 2, and then b times 2x minus 3. So first I'm going to let x equal negative 2. And that is going to give me negative 14 on this side. This term will go away. And if I plug in negative 2 here, that'll be negative 4 minus 3. So that'll be negative 7b. And so b is 2. And then I'm going to let x equal, for this one, that would have to be 3/2. And so let's see what we get there. 7 times 3/2, that would be 21 halves. 7 times 3 will give us 21. It'll be halves equals 3/2 plus 2. So that's 1.5 plus 2. That'd be 3.5, which would be 7/2. And then this term, thankfully, will go away. So these 2's are going to cancel. And then we get a is 3. So I'm going to put those back into these fractions, and I'm going to put all of that back inside of the integral. So it will be integral, what was a? 3 over 2x minus 3 plus b was 2 over x plus 2 dx. Now this one was a little tricky right here because you would need a u substitution. You would end up with the derivative being 2, and then you would need to adjust with a 1/2. So I'm going to have a 1/2 adjustment for this one because of the 2 there. So it's going to be 3/2 ln 2x minus 3 plus 2 ln x plus 2 plus c. So again, that was tricky. It was because of this 2 coefficient in here, we needed a 1/2 out front. All right, so now let's look at the choices and see which one that is going to be, that looks like A. But if you forgot about that 1/2, isn't that another choice? Because they always make like the simple mistakes be another choice. Yeah, like that would have been B. Evil, they're evil people that write these problems. All right, same thing for this one. I'm gonna write this off to the side. And so I want this to be something over x plus 2 plus something over x plus 1. And so if we multiply through by this common denominator, that's going to give us 2x equals ax plus 1 plus bx plus 2. And so we're going to let x equal negative 1. And that will give us negative 2 equals, this term will be gone. And if x is negative 1, this would just be 1b. So b is negative 2. And then we'll let x equal negative 2. So this side will be negative 4. And if x is negative 2, this would be a negative 1a. This term will go away. And so then a is 4. So I'm going to put those back into these fractions and put it back inside of the integral. So a is 4. And b is negative 2. So this will give us 4 ln x plus 2 minus 2 ln x plus 1 plus c. So let's see, is that D? Check the whole thing. Yes, that one is D. So the rest of these are review questions. Those were the only ones the College Board had, plus I didn't want to make you do like 7 of those because they're kind of long. So the rest of these are review questions, which is always good to review. All right, so we're given these values in the table. They're derivative values. So this is points that are on f prime. It says let f be a polynomial function, values of f prime selected are given there, which has to be true. I like to look at this, so I'm just going to go ahead and plot these points. It'll only take a second, and then we'll have a visual. Okay, not perfect, but good enough. Now, they tell us that this is a polynomial, so that means that it is continuous and differentiable. All polynomials are continuous and differentiable, so I know that I'm not going to have any asymptotes or breaks or holes anywhere in this. They're going to have to connect. So this is the f prime graph, and if I connect these, the graph is going to have to turn around twice. I'm going to change from decreasing to increasing at some point in here, and I'm going to change from increasing to decreasing at some point in here. And so that means that we're going to have 2 points of inflection. I just always tell everybody to write this out on like pretty much every piece of paper when they go to take the AP exam. It just helps so much. These were values for f prime, and since f prime changed from increasing to decreasing and decreasing to increasing twice, we know we changed concavity twice, and so that's 2 points of inflection that are in there. I can go through the other ones and show why they aren't as well. Graph being concave up would only be if, oh, actually, why did I just put that away? Let me pull that right back out. Graph would be concave up if f prime were increasing all the time, but we see we do have places where this graph decreases, so it can't be A. F is increasing where the derivative is positive, and that means above the x-axis. And at first glance, it might look like these are all above the x-axis, but we don't know what happened in between them. So like this graph could have come down here and come back up. So we don't know. So that's why it can't be that one. F has no critical point. So critical point would be where the derivative equals 0. And it looks like this doesn't touch the x-axis, but again, it could come down here. We just don't know what's happening in between. So there might be critical points. So it can't be that one. And F has at least 2 relative extrema. Now those would come from critical points. And I just said we might have them, but the other option is we might not have them. This graph might not touch the x-axis, and then we wouldn't have any critical points at all, so we wouldn't have relative extrema. We just don't know what's happening in between each of these points that they gave us, so you can't like make any assumptions about that. So anyway, I just wanted to go over why all those ones weren't answered. So the graph of the function f is shown. Where is f prime positive and increasing? Let me pull this back out again. F prime is positive where this graph is increasing. So we want a place where this graph is increasing. And F prime is increasing where this graph is concave up. So we want to pick a point where this graph is both increasing and concave up. So here we're decreasing. Here we're increasing, but it's concave down. Here we're decreasing. And here we are increasing and concave up. So that one would be. Right, number 5, if we go to plug in 0 here, e to the 0 would be 1. Cosine of 0 would be 1. And then 2 times 0 would be 0. So the numerator gives us 0, and the denominator is also going to give us 0. So we have indeterminate, 0 over 0, and so this is L'Hopital's rule. So we're going to do the derivative of the numerator and denominator. So derivative of e to the x would just be e to the x. Derivative of cosine would be negative sign. So those negatives are going to cancel. And then minus 2. And then in the denominator, we're going to have 2x minus 2. And so if we plug in 0, we're going to try again. If it comes out to 0 over 0, we can just do L'Hopital's rule again. I think this one works out though. Let's see. E to the 0 would be 1. Sine of 0 would be 0. And then minus 2. And then down here we'll have 0 minus 2. So that numerator is -1 and the denominator is -2, so positive 1/2. So that one is C. All right, number 6. I had typed this one in there for you guys because they just wrote it so small. F of 2 is 1, f prime of 2 is 4, and second derivative at 2 is 3. So we want to do the approximation of f of 1.9 using the tangent line. So one of these three is extra information. The one that we don't need to write an equation of a tangent line is the second derivative. So that was extra that we did not need. So this is our point, 2, 1, and this is our slope. Slope comes from the derivative, so that's 4. And so writing our equation, we'll have y minus 1 equals 4 x minus 2. And they wanted the approximation at 1.9. So I'm going to plug in 1.9, and then to get y by itself, I'm going to add over the 1. The reason we can approximate 1.9 is that it's really, really close to 2, and 2 was our point of tangency. That's where we wrote the equation. So as long as it's really close, then you're good. Now, I can't police whether you used a calculator on this at home, but this would be non-calculator on the AP exam, so we're gonna have to fight our way through this. 1.9 minus 2, that would be -0.1, times 4 would be -0.4, and so that would come out to 0.6. So that one is B. All right, 7, a polynomial has a relative maximum at -2, 4. I'm gonna graph these. So here's -2, 4. That's a maximum, so it's gonna do something like that. Relative minimum at 1, 1, so it's gonna do something like that. And a relative maximum at 5, 7. So something like that. And we don't know, you're probably like, why didn't she connect them? I don't know exactly what happens in between, but I know it's gonna have to do something like that. And no other critical point. Oh, actually, I do know what it's going to do in between, because if there are no other critical points, then the graph cannot turn around anywhere else. So this graph, those are the only turns that it can have. It's going to have to look like this if there are no other critical points. So how many zeros does the polynomial have? Well, this graph is going to touch the x-axis twice, so 2. And last one, a function f is continuous, so no holes or breaks or jumps or other problems, and has the values in the table. So again, let me graph these. I like having a visual for this. We've got 0, 1, and then 2, 2. And the point for 1, it's 1k. So we need to know what k is going to be. It says the equation f of x equals 1/2 must have at least 2 solutions. So here's the line for f of x equals 1/2. If that has 2 solutions, that means we have to go through that line twice. And so this point at 1 is going to have to be down here below 1/2. So the only choice that's below 1/2 is A, which is 0. So if I plot that there, when we connect these, we would end up intersecting that line at 1/2 twice. The reason 1/2 won't be good enough is it'll only hit once if it's on the line. To go through twice, it has to actually be below